Welcome back to Session 8 of the Fundamentals of IPOS. This is a momentous time because we have reached the final part of learning the language. This is part 5 of that. This also marks the midpoint in our course. When we're finished with this module, you will have all the information you need on the IPOS language itself, and then we'll be able to move on to motion control, which is really why we're learning this. So let's wrap up our final language session. What we're going to look at right now is something called looping structures. This is something very important in programming. You really can't write good programs without loops. So let's take a look at them. A loop is a block of code that just repeats either a fixed number of times or until a specific condition occurs. So there are really two kinds of loops, ones that count and ones that just operate until something happens and then they stop. Loops let programs solve problems through iteration, where they have to keep calculating something over and over or doing some operation repeatedly to sort of zoom in on a desired target. Sometimes loops enable the program just to wait for something to happen. They sit and spin their wheels until a certain condition is met. They very definitely reduce program size by executing the same piece of code over and over and over. Stop and think about it a second. If you couldn't do a loop and you had to do something 100 times, you'd have to put that piece of code in 100 times, and that would get really ugly really fast. So be glad that all programming languages include loop structures. The first kind of loop we're going to look at is called the conditional loop. It executes a block of code until something happens. That's the condition. And when the condition happens, then the loop exits and stops doing that block of code. I like to think of a conditional loop sort of like waiting at the gate at the airport. Everybody's sitting there doing different things, sort of spinning their wheels, waiting for the plane to arrive and the door to open and boarding to begin. And of course, once they open the gate, everybody gets up, lines up, gets ready to board the plane. So that's really what a conditional loop is kind of like. Now, all loops use evaluation symbols to determine whether the condition that the loop is checking is true or false. So all of these involve true-false operations, just like decision structures like the if statement. So they're not really interested usually in specific numbers. They're just interested in that yes-no condition. And for that reason, they use exactly the same evaluation symbols that you use with if statements. Equal to, not equal to, greater than, less than, greater than or equal, less than or equal. Don't forget that double equal is special. Don't use a single equal. That would be a big mistake. And then, of course, we have our logical operations, not, and or, which you can use to create expressions with more than just two components. Maybe you want to test several conditions all at once. You could and them or them together. If you need to invert something, you could use the not symbol. So this is really pretty much the same as what you learned for the if statement. The first loop we're going to learn about is called the while loop. This is a very useful loop. You'll use it a lot. It executes one or more lines of code as long as an expression evaluates to true. So let's look at an example. While h1 equals 0, do this one thing, and that is increment h2. Remember, if you take a variable and put a plus after it, it just adds 1 to it every time. So what this loop is going to do, it's going to just sit and keep incrementing h2 as long as h1 equals 0. The minute h1 changes to something else, that loop will stop, and it will exit, and it will continue with the line right after h2++. So this is just a very simple one line of code kind of loop. By the way, notice there's no semicolon after the while. There is after the h2++. And of course, as usual, if you have more than one line of code, then you need to use curly braces. So this is an example of a while loop with curly braces. Of course, remember what I've always said, you can always use curly braces, even with just one line of code. And I think that's kind of smart, because if you want to add another line, the curly braces are already there. Now let's look at this more complex loop. Notice it has two conditions. It's checking to see if h1 is greater than 5 and not H2, or H2 is false. So both those conditions have to be true because it's an AND statement in order for that while loop to keep going. So if either H1 becomes less than 5 or equal to 5, or H2 ceases to be false and becomes true, then that loop is going to exit. But as long as those two conditions are met, it's going to keep executing those 4 lines of code. Here's something else you should be aware of. A while loop doesn't have to execute at all. If the expression evaluates to false, the loop will just be bypassed, because it checks the test condition first before it executes any code. While H1 equals 0, it's going to do that test first before it increments H2, for example. So if that condition is already false, the while loop just drops out. So a while loop may not even execute. It just depends how your code's written. Let's look at a few nuances about while loops. This is kind of an interesting one. If you take a while loop and put a semicolon after it, it'll just wait and spin until its condition is false. For example, notice this while loop doesn't even have a line of code. All it does is it keeps checking H1, and as long as H1 is true, it's going to just keep looping to itself, not doing anything. It's basically just whirling in an endless loop. But the minute H1 becomes false, it'll drop out. So you can use loops like this for certain things. It does have an application. Another thing you can do is just put a permanent true in a while loop and turn it into an endless loop. The number 1 is a permanent true, so if you just say while 1, everything inside those curly braces is just going to execute over and over and over. Think about it a second. You've seen this before. There is one of these in the main function, and we use that endless loop to keep the code executing over and over, but we also use it to prevent the initialization code from executing more than once. So this does have an application, and you have seen it in use. Now there's a different version of the while loop called the do while loop. It's very similar, but it does have a few subtle differences. It too executes 1 or more lines of code while its expression evaluates to true. Let's see an example. This is just a 1 line of code do loop. Begins with the word do, then it has the line of code ending in a semicolon, and then at the end it has the while expression with the condition, which also ends in a semicolon. So it's basically saying do the loop while H1 is 0. So as long as H1 is 0, it's going to keep looping and incrementing H2. So do note that semicolon at the end. That's important. Of course, if you want to do multiple lines, you do the usual curly braces thing. So here's an example where it does a number of things in the curly braces, and it's got 2 conditions that it checks down there at the end. H1 has to be greater than 5, and H2 has to be false. As long as those conditions are both met, the do loop keeps going. Don't forget, of course, it ends in a semicolon here as well. Now, how does it differ from the while loop? Very simple. It checks the condition last instead of first. That means it will always execute its line or lines of code at least once, even if the conditions were never true. And that's because it does the test at the end. An ordinary while loop does the test first before running the code. So this is just a variation that in some situations is just what you want. So sometimes the one will be better than the other. So 2 tools in your toolbox. All right, moving on to a new kind of loop. This is called a counter loop. It is a loop that instead of waiting for something to happen, something to change from true to false, it just loops a specific number of times. It maintains a count, and it loops all those times, and when the count is over, it's done. There's one kind of counter loop in IPOS. It's called the for loop, and it requires you to dedicate a variable to it that maintains the count. We call it the counter variable. So here's an example. We're using H1 as the counter variable. So you just set up a variable to keep the count, and that's what it's for. Now you notice H1 appears in the for loop 3 times. And what are those for? Well, these control how the loop behaves. So let's see what each of the three does. Okay, the first one, h1 equals 0, that initializes the counter. That sets the counter to its initial value. In this case, to 0. You don't have to set it to 0. You can set it to any number you like, but 0 is common. So that is your first one. The second one is the test condition. h1 is less than 100. This is how the loop decides when it's done counting. So this loop is going to start at 0 and it's going to count until it reaches 100 and then it's going to exit. So as long as it's less than 100, it will keep looping. So it'll go 0 up through 99, it'll then become 100 and it'll exit. And then the third control component is called the variable change. And in this case, we're using that increment function, h1++, so it's going to increment the counter by 1. You can also use decrement, the double minus, so that makes the counter count either up or down. Not too hard. Do notice that we use semicolons internally to separate these. This is kind of weird since we think of semicolons mostly at the end, but they're used internally here. Notice also there isn't one at the end of the loop itself, although there certainly is one at the end of the line of code, the h2++. And of course, again, if you have multiple lines of code, you got to use curly braces. Here's an example of a counter loop that counts down instead of up. It starts at 25. It counts backwards by 1 for each cycle, and it will exit once it reaches 0. Do be aware, if you don't set your control values right, it's possible the loop won't run at all. If you initialize the counter variable to something and then set up the condition so it's never met, the loop will just bypass. So if you have a for loop that never seems to run, look very carefully at how you've set it up. You may have made a mistake. Now, what if you're in a loop and you want to get out of it? There is actually a way to do it. You can prematurely exit a loop by putting a break statement within the loop, and that will immediately exit the loop. Oftentimes what programs do is they use an if statement to check for some condition that would create that premature escape, and if it's true, then they execute the break statement. However, a lot of programmers really don't approve of doing things this way because it reduces readability. They view it as almost cheating. Many programmers prefer to build the exit condition into the loop structure itself so the loop can exit cleanly, rather than just jumping the fence, which is what break really does. Let me show you both ways of doing it. Here we have a for loop. It's counting starting at 0, and it's going to count up until 10, and then once it exceeds 10, it will finish. And it's doing a number of things, but one thing it does is it's looking at h3. And if h3 becomes true while all this is happening, it aborts the loop and jumps out. So this would give a premature exit if h3 becomes true. It would exit the loop early instead of going through the full count. All right, this will work. There's nothing wrong with it. It's perfectly legal code, but a lot of programmers think it's kind of sloppy, and they would prefer to do it this way. They would create a counter loop using a while loop, and they would take h1, set it to 0, and they'd make the while condition check two things. First of all, check the count. Is h1 less than or equal to 10? That maintains the count. And notice there's an and statement there that's watching the h3 variable. That h3 variable becomes true, then the while loop on its own will terminate itself. And that is considered the better way to do it. Notice we have to increment the counter variable inside the while loop. You see the h1++. So this does exactly the same thing as the for loop. Doesn't take really any more code, but it is considered a cleaner example because it's using the basic loop logic to decide whether or not to stay in the loop. And that's just considered a little better. All right, enough talk. Time for another program. You're going to create a new program called Program 7. And here's what I want you to do. I want you to use the loop structures, as you can probably guess. So here are the guidelines. Again, the program will be controlled by DI10 and DI11. You're going to use the digital outputs 10 through 17 and the lights attached to them. All lights should start out in the off condition. And then you're going to watch DI10 and DI11. Wait until they're both off. So if they happen to be turned on when you run the program, shouldn't do anything until they're both off. Then wait for an on-off cycle on DI10. You've done stuff like this before. This is nothing new. And then once that happens, I want the light to travel between DO17 and DO13. So it's going to go light up DO17, then DO16, 15, 14, 13, and then it's going to go back the other way, 14, 15, 16, 17. It's going to be a traveling light, okay? So the light will just bounce back and forth, do this kind of cycle. And I'd like you to pause 0.2 seconds between each position, 200 milliseconds. And if you turn DI11 on anytime when the light is traveling, it will complete the current cycle. That means it'll go back to DO17, and then it will go back to the program start and wait before doing anything further. Otherwise, it'll just keep traveling endlessly. And I want you to use looping structures, and this time you may not use the wait input function. So you'll have to come up with other ways to do some of the things that you did with that before. So, a little extra challenge. All right, pause the video, go do it. All right, let's see how you did. I'll show you how I implemented this, and then you can compare it to your work. All right, well, it's bouncing ball time. Our goal is to write a program that has a traveling ball that goes between DO17 and DO13 and just bounces back and forth. So we're going to get this set up. We have a couple interesting restrictions. We're not allowed to use wait input, but that's okay. There are other ways to handle its function. Let's go ahead and get started. The first thing we're going to do is set up our variables and constants. We're going to set up one constant for a delay. We're supposed to delay 0.2 of a second between ball positions as it moves back and forth. That's 200 milliseconds. We're going to create a constant for that so we can easily change that time if we wish. We're also going to set up a few variables, and I'm going to let IPOS pick where they go. So here we go. I'm going to explain these. Okay, so there's our delay constant, and we're going to create two regular variables. One is called ball loop. I'm going to use a for loop here, so this is going to be my for loop counter variable. And the second is ball position. This is going to be a variable where I store the location of the ball as it travels between DO17 and DO13. So two variables will be all that it takes. Now, the very first thing I have to do is turn off my lights and get everything set up. So here's what I'm going to do for that. I'm going to do all this inside the while loop. There really isn't any initialization that happens just once. Everything I do happens over and over again, so nothing will go right inside of main but before the while loop. We're going to do two things. First of all, we turn all the lights off just by setting opt-out p IPOS to 0. We've done that a bunch of times. But I'm also going to set my ball position to its initial position in DO17. Notice I'm using binary here again, and that's because opt-out p IPOS has 8 bits that are associated with the IOs and therefore the lights, and what I'm doing is I'm putting a 1 bit in the DO17 position. That's the 8th bit position, so that's the first light that's going to be turned on. All right, now we have to get around the fact we're not allowed to use wait input. Here's what we're going to do instead. Remember the requirements. We need to be sure that first of all, before anything happens, both DI10 and DI11 are off. So we're going to use one of those one-line while loops to handle this. Remember, a while loop, if it has a true in its parentheses, will just keep looping. What we're going to do is we're going to keep looping until DI10 and DI11 are both off. Here's how we'll do that. We say while DI10 or DI11. In other words, if DI10 is on or DI11 is on, or they're both on, just keep looping. And this is one of those while loops that doesn't even have a line of code. It just has a semicolon at the end. So it's just going to sit and spin until DI10 and DI11 are both off. That's the only situation that'll produce a false and cause the while loop to exit. Okay, so that's going to watch our switches. Now the next requirement is we need to wait until DI10 goes on and then off. Remember, we have to toggle it. So we're going to need to use 2 more while loops, as you can guess. So let's put the next one in and I'll explain how it works. Okay, so this one says while not DI10 or DI11. What's it going to do? It's waiting for DI10 to go on. If DI10 is off, that's going to keep the while loop true and it's going to keep spinning. But notice we're also checking DI11 because we don't want DI11 to go on. DI11's got to stay off. So if the user turned on DI11, that will also make this loop true and it'll keep spinning. The only way it's going to get out of this loop is if you turn DI10 on and DI11 stays off. Now we're going to put our third while loop in here that will look for DI10 to go back to the off condition. While DI10 or DI11. In other words, if DI10 is on, it's going to make that while loop true and it's going to keep spinning. And if you switch DI11 on, it's going to make it true and keep it spinning. The only way to get out of here is to have DI10 become false and DI11 to stay off and also be false. If they're both false, it'll get out of the while loop and be ready to go. All right, so we have circumvented the need for wait input. Notice also, by the way, we're using these predefined DI10, DI11 constants. Remember I showed you those in the last session? They're defined in IOB.h, which we included. If you look up there, you can see IOB.h. And all this is doing is this is looking in the right system variable and masking off just the bit we care about. So remember, this is that handy little shortcut, the one I showed you with the Swiss Army knife. We're using those here. And that saves us the trouble of doing all that bit masking ourselves when we just want to read our standard IOs. We're now ready to start the ball bouncing. So what next? Well, what we need to do is we need to display the ball in the first position, and that is DO17. That's the position on my control box that's on the extreme left. So here's what we're going to do now that we've finished waiting. We're going to set opt-out IPOS to ball pass. And remember, we've just set that a little earlier to have a 1 in the DO17 position. So that's going to light up the ball in the initial position. And then, of course, we've got to delay because we're supposed to always wait. Let's go ahead and wait. And we're using that delay constant with our wait function. That's our first position. Now, we need to make the ball travel. It's going to go through a total of 5 positions, DO17, DO16, 15, 14, and 13. Then it's going to reverse direction and travel back. We're going to use a for loop to do this. However, before we can use our for loop, we've got to take care of one other situation. Remember, that ball is supposed to just travel back and forth endlessly until we switch DI11 on. DI11 is kind of like the stop switch. We need some way to detect when DI11 goes on and stop. But we don't just stop instantly. We wait until we've completed a travel cycle. In other words, traveling to the right and then back to the left, and then we stop. We're not just going to break out of it at any old time. We're going to break out of it only at a specific place. Let's do this instead. We're going to use another while loop. And here it is. And I'm going to put a closing curly brace here just so I never forget. It's always smart to put your curly braces in pairs so you never forget. All right, what we're going to do after displaying that initial ball position, we're going to check DI11. And as long as DI11 is not true, that while loop is going to execute and the ball will travel. But the minute that switch goes on, the next round of the while loop, it's going to just exit. and go back to the beginning and reset and be ready for another cycle. Okay, we're going to put this in here. Now we're going to go ahead and do our traveling ball logic. And we're using a for loop for that, as I said. Here it is, along with its accompanying code. Let me talk you through this. All right, the ball loop is initialized to 0, and it's going to cycle until it becomes 4. It's going to go from 0 and then count to 1, 2, 3. It'll become 4 and exit. So it's going to go through 4 cycles total, 0 to 3. The ball's in the first position. We've got to move to the next 4. Notice we're using that increment instruction ball loop ++ just to increment it. That's our loop. It's going to cycle 4 times. Now, what's it going to do inside the curly braces? It's going to do 3 things. It's going to take the ball position and shift the bit right. It's going to just move that bit into the next position, and that's going to cause it to effectively travel through the variable. Then we're going to take that variable and we're going to copy it, ball_pos, into opt-out PIPOS, which will display the ball. We'll wait for our delay of 200 milliseconds, and then we'll go through our next cycle of the loop. That's pretty simple. So the ball is going to travel from left to right. It's going to go from DO17 down to DO13 over a total of 4 cycles. Then it's got to head back the other way. So we need another loop that pretty much does the same thing, except shifts the bit in the other direction. We're going to put another for loop in here. And there you go. You can see it's exactly the same code, except it's shifting left instead of right this time. There we go. Let's just clear up this extra blank line. And that is it. That's our code for our traveling ball program. What should happen when we run this is we have to make sure DI10 and DI11 are both off. Then we take DI10, we turn it on and off. The ball is going to start traveling back and forth, and the only way to stop it is to flip DI11 on. And as soon as it's completed one back and forth cycle, it'll exit that while loop, it'll go back to the beginning and wait for both switches to be off before it can do anything again. And then, of course, we could trigger it one more time. Let's compile it, make sure that the code is good. And it is. And we're now going to run it, and we're going to flip our switches and see if it works. Here we go. We'll start the program and we'll go flip the switch. We can see that ball is traveling back and forth. It will do this forever until I switch DI11 on. So I'm going to stop it with DI11 now. And there, you notice it stopped when it completed a cycle. Now, if I want to trigger it again, I have to turn DI11 off and then cycle DI10. And we can see it's working just fine. And there we go, one working program. Okay, last section of our little diagram here, we're going to learn about user functions. This won't take long. A user function is a custom block of code that you create yourself to perform a specialized task. We've been using some of the built-in system library functions. These are functions that you create to do your particular activities. They certainly make your program more readable because you can break your code up into smaller blocks that do very specific things. And if you do the same thing in several places in your program, it makes sense to create a function. You just call it every time you need it. One thing you should be aware of, this differs from the system functions. You cannot have parameters in the parentheses with your functions. There are no parameter lists, so you can't pass values into them. Now you may be thinking, well, in that case, how do I control them and modify their behavior? Well, the answer is, since all the variables in IPOS are global, that means they can be seen everywhere. You can dedicate variables in your program to pass information into functions. So you create a variable in the beginning, and then right before you call the function, you set it to a particular value, call the function, and the function code will then go to that variable to look for settings that will modify its behavior. So that's kind of a way to work around the fact you can't have parameters. I would also suggest you never begin a user function with an underscore. That's just because the system library functions begin that way, and it makes more sense not to create confusion by using underscores. So don't do it. And I would suggest either all lowercase or mixed case in names, but never all uppercase. Again, that's just a common convention. All right, here's an example of a user function. What I do in my programs is I create a section near the end and I put a comment header there to identify that all the functions after this are ones that I've created. And then each individual function gets a header where I identify its name and give it just a brief description about what it does. And then my function follows. This is just good documentation, makes your code easier for other people to interpret. Notice you must have empty parentheses after the function name. That indicates there are no parameters. Don't forget those parentheses. And of course, your code is contained between curly braces. No big surprise there. Now, when you're ready to use your function later in the program, just call it by name, just like the built-in functions. So there's my function goIndex. So just call it. Do note you must have that empty set of parentheses there to indicate no parameters. That's pretty much it. I told you it wasn't too complicated. So let's go ahead and do one more hands-on task. You're going to take your existing file, program 7, and you're going to make some changes. I'd like you to create a user function called delay. And it should delay in multiples of 10 milliseconds. So you're going to be passing in a delay value, number like 1, 2, 3, or 4, etc. And for each of those, it'll delay in multiples of 10. So if you pass in a 1 to it, it will delay 10 milliseconds. If you pass in a 2, it will delay 20, and so on. Now, of course, you can't pass in the delay by a parameter because you can't have parameters with user functions. So you're going to have to create a dedicated variable, which I suggest you call delay time, and that's how you'll pass in the delay value. And then take your existing program with the traveling ball and modify it so the ball delays 300 milliseconds when it's moving right and 150 when it moves left. And you can use that delay function instead of the hard-coded values you probably used in the previous iteration of the program. Okay, pause the video, do it, and we'll come back and see how you did. All right, hope that went well. Let's take a look at my code and you can compare it to yours. Well, according to our instructions, we're to take our existing program 7, which is our bouncing ball program, and just modify it slightly. Instead of using the regular wait function with a fixed value for all the ball travel times, we're going to create a user-defined function that will allow us to produce a variable delay, and then we're going to use a different travel time for each direction. What we're doing doesn't vastly improve the program, it really just gives you a chance to play with creating your own functions. We're going to go ahead and create our own function. The first thing we're going to do is delete our delay constant because we don't need it. But we need to add an extra variable because we are going to need a general purpose loop variable. The first thing we're going to do is just add another variable here, and again we'll let IPOS decide where it goes in the data memory. And I'm just calling this loop 1, and notice my comment says it's a general purpose loop counter. In programs it's often very common just to need a loop to do something, and once the loop is over you don't need that variable anymore. So if you just create one of these general purpose variables, you can use it all over your program. All right. We've got that in place. The next thing we have to do is create our user-defined function. We're going to go down here to the bottom. And remember, I've created a comment that identifies where the user functions begin. I'm going to add some blank lines here, and we're going to put our user-defined function down there. Let me paste it in here, then I'll explain how it works. And there we go, there's our user-defined function. Notice that I always comment my function with a header. I give the name of the function and then just a brief description of what it does. In this case, this function is called delay, and it pauses for x times 10 milliseconds. Remember, we're going to pass a value in through a variable, and we're going to delay whatever that variable is times 10 milliseconds. This will allow us to adjust our delay time. Now, how do we do that? Well, it's really simple. What we're going to do is call the wait function with a value of 10, and we're going to put it inside a for loop. And the for loop will just loop repeatedly, calling that function over and over and over again, producing a series of 10 millisecond delays. It's really pretty simple. Let's just talk our way through this for loop to make sure you understand it. Notice we're using our general purpose loop variable here, loop 1. We initialize it to 0. And our condition for staying in the loop is that loop 1 has to be less than the delay time. As soon as it equals the delay time, the for loop will terminate. And of course, we increment the loop counter through every pass by using a loop 1++. We only have one line of code, so we didn't need any curly braces, and that's our wait 10. Now let's just think about what would happen. Let's say we set our delay time variable to 1. All right, the loop would initialize as 0. It would do a test and say, is loop 1 less than delay time? In other words, is 0 less than 1? The answer is yes, it is. So it does the wait 10. Then it increments the loop counter, so loop 1 is now equal to 1. It asks the question again, is loop 1 less than delay time? Is 1 less than 1? No, it's not. So it exits, and that's the end of the for loop. And we just did one pass, which gave us 10 milliseconds. That's exactly what we want. If we set delay time to 2, it would go through that loop twice, and we'd get 20 milliseconds, and so forth. One thing we need to go back and do, however, is create that variable delay time. Delay time is how we pass in the amount of time we want to delay. Remember, you can't pass in parameters in user-defined functions, unfortunately. I don't know why that feature got left out. It would have been handy. So let's go back to the top and create delay time. There we go. There's delay time. That's our delay multiplier. We're almost ready to use this. Now we just need to go into our code and replace those fixed delays with call to our function. Here's our first one right here. Let's just delete that line of code. And we replace it with 2 lines of code. We set delay time to 30 because we want our ball to delay 300 milliseconds when it's traveling right and a shorter time traveling left. So we set it to 30. 30 times 10 is 300. Then we call our delay function. Notice we have to put those empty parentheses after it, so don't forget that. And of course, a semicolon. That's our first one. Now we go down here, and we're still traveling to the right. All right, so we'll delete this line of code. Now, here's something we're going to do. We're going to save ourselves a line of code. We're not going to keep setting delay time to 30. We're just going to set it once before we jump into the for loop. So before that for loop, we set delay time to 30, and then we call our delay function right in here. And we're going to do the same thing for the second for loop when we're traveling left. Of course, we're going to use a different delay time. We're supposed to use 150 milliseconds, which would be a multiplier of 15. We'll get rid of this line of code and replace it with our function. And that is it. Pretty simple. Let's compile it. Compiles fine. We'll run it, and we will confirm that our ball travels more slowly as it goes right and then more rapidly as it goes left. I'll start my program. And that definitely works. So you now see how you can create your own functions. Admittedly, this wasn't a very exciting one, but it's a beginning, and it gives you an idea of how to add yet one more tool to your IPOS toolbox. All right, we're almost done. Just one last thing. This has nothing to do with functions. This is just the place I thought we could tuck it in. I want to show you one more debugging tool built into the IPOS compiler that helps you debug your programs. Now, so far, when you've been running your programs, you click the lightning bolt and they just take off and start executing. But sometimes it can be really handy if your program's doing something weird to run it one line at a time and kind of watch what's happening with each line. That's called running the program in single step mode. It's executing it just line by line, and you have a button you click. Every time you click, it runs one line of code. So that's very handy if your program's doing something mystifying. So how do you do single stepping? It's really simple. The blue bar that will appear in your code shows the line that's going to be running next. So in this case, h0 equals 50 will run next. And what you do is you click the Execute Single Step button, which is right up there. You do that instead of the lightning bolt. And it will execute the line underneath the blue bar, and then the bar will move to the next line and wait. And when you click the button again, it will execute that line and so on. So that is a really good way to run your code basically very slowly so you can see what's happening. Another thing you can do that's helpful is you can run your program up to a breakpoint. Maybe you don't want to sit there clicking that single step button hundreds of times. You want to run a block of code but then pause partway through. If you want to do this, you set what's called a breakpoint. You mark a spot and your code will run. It will run up to that point and then it will pause. The way you do that is the blue bar shows where the next line of code is going to be run. And what you do is you put your cursor one line past where you want the execution to stop. So if you want your last line to be that h2 minus equals h0, then put the cursor on the line right after that, and then press the Go To Cursor button up there. It will execute all the lines of code to the line right before the cursor, and then the blue bar will move to where the cursor is and stop and wait. So that's another way of running the code, not continuously. So it's going to execute those lines if you put the cursor where it is there. Now, a really power developer way to use this tool and one other is to open up a variables watch window and then either single step the program or run to a breakpoint, and then you can watch the variables changing too. And usually between looking at the variables and single stepping or running to a breakpoint, you'll be able to figure out what is not working. So this is a very good strategy once you learn how to use it. And so I'm going to demonstrate it. I'm going to take one of our programs and I'm going to run it and show you these different modes. You can play with it on your own. So let's see it in action. Let's take a quick look at the single step and breakpoint debugging tools. As I said, these can be really helpful if your program's doing something strange. What I have done here is I have returned to our very first program, the mystery program, program number 1. So I've loaded that up, and of course I have to compile and transfer it into my VFD, which I've done. Now you notice that blue bar there. Of course you've been seeing it every time you've been compiling your programs, but now you understand it's telling you where the program execution will begin. So what we're going to do first is just single step the program, and then I'll show you how to run to a breakpoint, and then lastly we'll look at how to use the variables watch window to sort of give us extra debugging power. All right, instead of doing the usual thing, clicking the lightning bolt, which would just run our program normally, I'm going to go to this button over here, Execute Single Step, and I'm going to click it. And every time I do that, the blue bar will advance one position and it will execute the line of code that it's currently under. So you can see the very first thing it did is it executed opt outp IPOS equals 0. Then it went into that while loop because the while loop is always true. And now it's sitting here waiting for me to turn DI10 on. Notice if I just keep clicking it, nothing happens because of course that switch is off at the moment. So I have to go to my control box, turn that switch on, and then the next time I click, we should be okay. And you can see now we moved to the next while loop, but of course now it's waiting for that switch to go off. Every time I click it, nothing happens because it's just sitting spinning in the while loop. So now I've got to turn that switch off, and you can see now we move on. And as I click now, we go from line to line to line. We move into the for loop. and we just continue executing lines of code. And I don't have the camera on, but the lights are changing when we get to lines that change them. So you can see this is a way of just going through your program very slowly, running it one line at a time, which can be really helpful. Now, once you've solved your problem or you're tired of single stepping, if you click the stop button, it sort of resets everything, puts the blue bar back to the beginning of the program. And at that point, you could make changes to your code. You could go ahead and run it in normal mode. Doesn't matter, everything's available to you. Now let's go ahead and look at the run to a breakpoint option. Remember what I told you a few minutes ago, to run to a breakpoint, you have to set where the breakpoint is, and you do that just by positioning the cursor to the line after the last line you wish to run. What I'm going to do is I'm going to say I'd like to stop on this line right here. H0 equals H0, shifted to the left by 1. What I'm going to do is I put my cursor the line right below it on that if statement. And then I go ahead and go up here and I click Go to Cursor. And it will run up to that point and then stop. So I go ahead and I click Go to Cursor. And what is happening, although you can't actually tell, is that the program is waiting for me to flip DI10 on and then off. So I better do that. And now the blue bar appears, which means that the program has run all the way through the line before the blue bar. It is now stopped on the blue bar line. It hasn't executed it yet, and it's waiting for further instructions. At this point, I could do anything else I want, but I'm just going to click the stop sign, which again resets things. So that is running to a breakpoint. Now let's look at our third possibility, and that is using either single step or run to a breakpoint in combination with the variable watch. What I'm going to do here is I'm going to bring up the variable watch window. So I'm going to pick Open Window. And it just so happens that it still has the variables set up in here that we were looking at last time we used this. And it has H0 in binary mode, which is the one that controls the lights. I'm going to show you what happens when I step through it. And you'll actually see the bits shifting back and forth in there as I run it, which is kind of neat. It lets you know what's going on. However, I need to show you a little bug, or possibly it's a feature, in the IPOS editor that can really confuse you if you don't know about it. You cannot have the variable watch window on top of the editor window when you're trying to single step or run to a breakpoint. If you do it, for whatever reason, those buttons that control it get grayed out. And that can be very mystifying. So here's what you have to do. You've got to make sure the two windows don't overlap each other. So what I'm going to do here is I'm going to just slide the edge of the editor window away. And what happens now is the variables watch window is all by itself on top of the IPOS compiler window, but the editor window is separate. Now I'll be able to go ahead and run both at once. What I'll do here is I'll run it in single step mode. So I'm going to click the editor window to bring it to the foreground, and you can see now my buttons are not grayed out. And I'm going to now click single step. And of course, I've got to get past that while loop, so let me turn DI10 on and then off, and we'll get past it, and then we'll watch what's going on. I'm past it now. Go ahead and watch in the variables watch window. I know it's not in the foreground, so it's a little bit light, but you can still watch the bits. Watch H0. I'm going to start clicking this button a bunch of times. And we're going one line at a time. And as soon as we come to that shift instruction, you notice that one bit moved to the left. And every time we get past that, it's going to shift again. You can see it's moving. So you're seeing the different variables changing in response to what's going on as you're single stepping. This is a very powerful combination. You can see what the variables are doing as you run the program slowly in this way, and hopefully then you can spot problems. And that is it. That's the final debugging tool that I'm going to show you. We're done. Okay, well, I hope you found that interesting and useful. So now we have reached a moment where we're all going to cheer, because that is it for the programming language part of the class. you have now learned all the bedrock of IPOS, the structure upon which you're going to build motion control applications. So you're at the halfway point. Give yourself a big pat on the back, drink some coffee, and when you come back, we're going to look at motion. We're going to start spinning the motor. So that is the end of session number 8. And once again, let me just say, good job.